Okay, today we keep talking about software security. We will discuss return-oriented programming. Then Wednesday we will talk about heap-based exploitation. Then we move to network security topics. So last class we already took a look at buffer overflow, especially overflow the code pointers, especially the return address on the stack. So this technique can be used to do something called a return to libc attack. Basically, you override the return address to a libc function, and just it's kind of like you are calling that libc function. So libc functions, there are many wrappers of system calls. So because of that, the attacker will have the ability to directly communicate with the kernel. You can start a new process. You can make other system calls. So today we will talk about return-oriented programming, which is a discovery made in around 2009, or maybe a little bit before that. And this is one of the greatest discovery in system security or software security in the last 15 or longer years. So with the return to libc attack and with the buffer overflow, what we can do is we can inject code onto the stack, which in this class I didn't really show you. In the software security, we do that. So in the code injection attack, we can inject some arbitrary code, which we call share code, onto the stack or onto other places. Then we redirect the return address to that direction, to that location, and start execute from there. Then the share code can make arbitrary system calls, can run arbitrary code in userland, basically. However, there are limitations of this attack. First of all, this kind of attack was discovered back in the 80s or early 90s. Then, since then, CPU and OS have changed a lot, have improved a lot to defeat this kind of attack. First, the CPU introduced a feature called data execution prevention. The principle behind that is everything on the stack is supposed to be data. You should never put code on the stack. Code should just be in the .code section, the text section. Because of that, the CPU add a feature that the CPU would not execute anything on any data section. There is a bit in the memory management table to show whether this part is executable or not. So because of that, code injection attack doesn't really work. That's why we need a new class of attack for attackers. This is called the code reuse attack. In code reuse attack, the attacker doesn't need to inject any code into the address space, but to reuse whatever is already in the address space. Return to libc is actually a code reuse attack. The attacker didn't reject any code to the target address space, but reuse the C library functions that are already there. However, there is a granularity issue. We are reusing functions in the address space. We are not using something smaller than that. Then we can defeat those attacks. For example, we do not allow return to those specific locations. However, later, in 2009 or maybe earlier than that, people discovered the return-oriented programming, which can find smaller gadgets, not whole functions in the address space. And the attackers can glue those smaller gadgets together to do arbitrary computation. So that's what we're going to learn today. Related to return-oriented programming, there are other ideas like jump-oriented programming, call-oriented programming, or even seek return-oriented programming. We are not covering those in the class. I have seen a lot of discussions in those kind of tags in papers, and we are doing some of that in our CTF experiences, but we're not covering those today. So the idea of ROP was, or return-oriented programming, was first introduced in 2005 to work around 4-bit architectures that require parameters to be passed using registers. The first paper on the attack itself was published in CCS 2007. Okay, so earlier than 2009. 2007. And the paper title was The Geometry of Innocent Flesh on the Bone. Return into libc without function calls on x86. So this was a single author paper by a professor at University of California at San Diego at that time. He moved to UT Austin several years ago. So the professor, he made a lot of contributions in system security and also crypto, I believe. So look at the title. The title is Geometry of Innocent Flesh, so on the bone. So the innocent flesh on the bone here means those gadgets in the address space. So those gadgets in the address space, they are not malicious code. They're just some instructions. But if we can glue them together, we can do something malicious. That's basically the meaning of this. So when the paper was published, he was still using return to libc. But return to libc, we are returning to functions. But here we are not returning to functions anymore. We're returning to gadgets. That's why he called that return to libc without function calls. The first version of this attack was implemented on x86, your laptop, most of your laptop. Later, we find this works on all other architectures, ARM-based, MIPS-based. So this is the original paper, 2007. That's a professor. Basically, he discovered that, well, like we said before, in 2005, we already have some ideas. This may happen in 2007. This paper proved this works. So he basically proved that in any sufficiently large body of x86 executable code, there will exist sufficiently many useful code sequences or code gadgets that attackers who controls the stack will be able to, by means of return to libc techniques, to cause exploited program to undertake arbitrary computation. So this is Turing complete. You're not really injecting any code. You are just reuse some code gadgets, some random bytes on the memory, but this turns out to be Turing complete. You can do whatever you want. 10 years after this paper was published, this paper received a Test of Time award at the CCS 2017. You can say he was the only author on this paper. So he probably realized that this is a very important discovery and didn't include anyone, but just published, he was already a professor, but he published this paper by himself. If you want to learn more about this, there is actually a journal version of this same paper with more authors. So the journal version was published in TSEC, I believe 4 or 5 years after the original CCS paper was published. So how does this work? Let's go back to where we left off last class. Last class, we talked about the 32-bit x86 machine. We can chain unlimited numbers of functions together. We return to each of them as long as they do not have arguments. Even if some of them have arguments, we can chain some of them together. So we can return to them one by one. we use this technique to print out knowledge is what? Knowledge is power. Francis Bacon, right? We use that to print that. So in ROP, we do not return to functions. Which means we do not return to the beginning of the functions. We do not care about functions. We return to some special code gadgets or code sequences. And all those code sequences or gadgets, they should end with a return instruction or a jump instruction. If it return with a jump instruction, we actually call it a jump-oriented attack. That's a little bit different technique. So in this class, we only talk about they end with a return instruction. So think about the whole address space. So how many pieces of code will eventually end with a return instruction? So most functions, or the functions, eventually, they will end with at least a return instruction. Maybe the function have several branches, they all return, then there will be return instructions. Those are return instructions intended by the compiler. When you code in C or whatever language, compile to binary, eventually, there will be return instructions. Those are intended, okay? However, there are actually more return instructions than that. Most of them were not intended return instructions. So after all, what is a return instruction? For the CPU, the return instruction is just some encoding, right? It's just some bytes. And in x86, return instruction can only be those 4 different bytes. It's either C3 in hex, 1 byte, that means return instruction. Or CB, one is for near core return, another one is for far core return. But anyway, they're just a return. Or they can have a return with some numbers to balance the stack. So it can be, the instruction can be C2 and a number. This number will be 16 bits, 2 bytes. So that's the only 4 possible cases for return instructions. However, obviously, x86 instructions, they are variable lengths. Some of the instruction is 1 byte. We saw that, like halt instructions. Some of the instructions could be 11 bytes or even longer, which means they are not aligned. Okay, it's not like the ARM instruction or MIPS instruction. So every instruction should start at address 0, address 3, address 7, like that. They are aligned. So x86 instructions, they are not aligned. The start of the instruction could be any address. The reason they design this is they want to make the instruction set condense and the compiled binary smaller. So maybe you learned something like Hoffman encoding. Yeah. So in Hoffman encoding, what you do is you encode different letters with variable lengths of bits. The one you use very often, you just use 2 bits, 3 bits to encode that. The ones you do not use very often, you use 5, 6 bits to encode that. So eventually, because they have different distribution, eventually you can make your, let's say, text file smaller. So here, similar idea. First of all, some of the instructions, they are used more often, so we want to encode them with shorter bytes. Some of them we do not use it very often, then we can encode them longer. And also, some of the instructions, they do not need any parameter, like a halt. Some of the instruction, like jump to a location, there has to be a location, right? So those are much longer. So because of that, any instruction, they may have those bytes as the data, not as the opcode. Let's say you have an instruction jump to the address, and the address has C3 there. then then in that instruction, there is a byte, C3. However, if your CPU start execute at the address where that C3 byte is, the CPU will interpret that as a return. The CPU will not interpret the whole instruction as a jump what instruction, right? So that's why there are many unintended return instructions in the addresses, in the address space, much more than we expect. So on our server, we install those tools. We will show you later. There are many tools we can use actually, but let's talk about this later. Here's another example. Let's say we have some byte sequence. They will have 8 bytes here. So the top is the lower address, the bottom is the higher address. So the byte sequence is 4031C0 this way. So if the CPU starts execute at this address, CPU will try to interpret what is the next byte. Is that an instruction? Then the CPU will find out this is an instruction, and the instruction is increase EAX. Then the CPU go to the next byte to say if this is instruction, which is probably not. Then the CPU will take 2 bytes to say if this is instruction, and find out this is exclusive or EAX. After that, it find out the next 5 bytes is an instruction move this number to EAX. That's it. So what if the CPU do not execute from here? In last class, we say that we can change the return address on the stack, which means we can ask the CPU to execute from wherever we want. So if the CPU was supposed to execute from here, now we change it. We ask the CPU to execute from at the middle of somewhere. So let's say we ask the CPU to execute from the 5th byte instead of the first byte or the 4th byte. So actually, we are jumping into the middle of the 3rd instruction, right? So when jump into here, the CPU start to execute from here. It says AB, and the CPU says, "Oh, I know this instruction. This is a store instruction, storing things from AES to where EDI points to." Then after that, then we say a C3. And the CPU will interpret this as a return, okay? Even though when your compiler generates this, when you write the code about this, this is actually a move a number to EAX. It was not intended to be a return instruction. It was intended to be the operand of an instruction. So the idea of ROP is to find out all those instructions, all those gadgets, code sequences, instruction sequences that lead to a return. And those will be useful gadgets. And next, let's say how we can use those gadgets. So we are going to use a simple example to show how this works. We are going to do a return to libc or return to any function on x64-bit version. So remember that. So last class we saw this example. We only saw how the 32-bit version works. So we have the main function, print out a function where print secret is. Then it calls the val foo, then print IP to the foo. The val foo is a valuable function. It has a buffer, 6 bytes in SQL level. Then it calls get, which you will input from terminal, stdin, which will overwrite the buffer. And after you override the buffer, you will overwrite the saved EBP. You can overwrite the return address as well. That's 32-bit version. 64-bit version, you write the saved RBP and also return address. Both of them will be 8 bytes each. Your goal is to overwrite return address on the stack of a val foo and return it to the beginning of print secret. After you get to the beginning of secret, this function will check if those two parameters are 1, 2, 3, 4 or deadbeef. If they are, it will print flag, right? So last class we say that if you want to go to the beginning of print secret, you need to put I and j, those two parameters, onto the stack. And I showed you where they were on the stack. And you can override them because they are on stack. They have a higher address than the return address. However, for 64-bit version, this is basically how the 32-bit works. You have the buffer. You have some room here, maybe some room here. Then you have saved EBP return address. Higher than return address, you have parameter I and parameter j. So as an attacker, when you overwrite, you just overwrite the whole thing here, right? The buffer, you don't care about what you overwrite. Return all of this part, you don't care about what is the value you overwrite. The return address, you will put the print secret here. Then those two parameters, you put their address there. However, this approach would not work for 64-bit machine. The reason is in 64-bit machine, the default convention, we do not use stack to pass the arguments. The bug here is a memory corruption bug. It's a memory-based buffer overflow. You can overflow the memory, but you cannot overflow the registers. Registers are part of the CPU. Memory is technically a device outside of the CPU. So in x86, the first argument will be in RDI. The second argument will be in RSI. Then in that order, we have up to 6 arguments in registers. If you have more registers, we do not have enough. If you have more parameters, we do not have enough registers, then we will use stack to pass that. And because of that, you cannot set argument 1 and argument 2 because they are not on memory. Okay? That's why we rely to something called the return-oriented programming. And this is how it works. So basically, I already gave you the, let's say, the share code, the exploit here. And let's try to understand why this exploit would work. So on the left-hand side, we have the 64-bit. Yeah, this is a 64-bit. You can say this is RBP, not EBP. Left-hand side, we have the 64-bit disassembly of the code. Right-hand side, we have the stack. So this one is, the top is the higher address. The bottom is lower address. This is a stack. So let's see where we are. We are at so the stack, look at the stack right now, we're basically at here. The last instruction return of the vulnerable function here. So at this point, we have already, because we already called a valfoo, so we already overwrite the stack. And we overwrite the stack like this. The buffer, we have a sequential override ability starting from the beginning of a buffer. And when we look at the disassembly code, you can see the buffer is actually at, so it should be valfoo. So here, this is where the buffer is. Buffer is at RBP -6. So exactly, we ask for 6 bytes, compiler gave us exactly 6 bytes here. So we overwrite from the buffer. Then we overwrite the saved RBP. However, those two values, we don't care. That's 6 plus 8 bytes, 14 bytes of basically garbage there. Then after that, this is the original, where the return address was. Instead of directly overwrite this address to the beginning of print secret, we put the address of a gadget there. And that gadget is pop RDI return. That gadget only has 2 instructions. That gadget is not here, okay? The address of the gadget is here. That gadget could be anywhere in the memory as long as it's executable. The gadget doesn't have to be an intended compiler-generated sequence like this. It could be just a data in operand in an instruction. However, there is a C3, and after we compile that, it has a C3, and that C3 can be a return. Then after that, we can have 8 bytes of this number, which is 1, 2, 3, 4, 5, 6. But here it's 8 bytes, not 4 bytes. That's why we have some leading zero there. Now after that, we have a pop RSI return. Then we have deadbeef. Then we have the address of return secret. Okay. Then let's see how this works. Okay. So now the CPU is about to execute the instruction return at the end of val foo, and the stack looks like this. So RSP points to what originally was the return address. Since we are about to execute the return instruction, what the return instruction does is to simply pop this address to RIP, right? So after we execute this return instruction, what happens is RIP will have the address of this gadget, which is pop RDI. Then RSP will move 8 bytes higher to here. Then after this, what is the next instruction to execute? What is the next instruction to execute? Previously it's here, which is so val foo was called by main function. So if we didn't override this, after this return, we're going back to main function, right? However, we override. So what is the next instruction to execute here? Yes. What exactly is that instruction? Exactly. So the next instruction we are going to execute is pop RDI. Okay. So pop RDI will pop whatever is on the stack to the register RDI. So what we're doing is we're popping this value to RDI, right? RDI is actually the first argument for that parameter, for the function. So after that pop, RSP moves up 8 bytes again. Then after this, what's the next instruction to execute? No, actually, the next instruction will be return, because with pop RDI and return, right? They are sequential. So the next instruction for us to execute is return. So now return what does return do? Return will pop whatever RSP points to RSI, RIP. Okay. So RSP points to the next gadget's address here. So that address will be moved into our IP after this pop. The RDI already set as this value. So then the next gadget we have is actually pop RSI. Then when we execute pop RSI, we're going to pop deadbeef into RSI. Then after that, we're going to execute return. So the next instruction to execute is return again. Return will pop whatever on the stack to our IP. That's why we put print secret address here. So after this, we are going to have the address of the function print secret in RIP. And also at the same time, we will have those 2 arguments in the register RDI and RSI. That is exactly what we want to set up that. So after that, we'll just return or calling into print secret, and print secret will compare those 2 values. They match. Then we're going to they match. Then we go Then we keep going and print out the flag for us. So that is basically how it works. So let's see if we can get this running on our server. Let's try this. Our server has been rebooted several times, so some of the address may change. We may need to work on that. So this one is return, which one is it? Overflow return 3, 64-bit. Overflow return 3. Here, this one, overflow return 3, 64-bit. So this is a set UID program, 64-bit. We can do a file on this. We do a file on this, and the file tells us this is a 64-bit machine, for 64-bit executable, dynamically linked, and this is the interpreter. If we do a LDD on this, it will actually tell us it's using this C library, and the C library will be loaded at this address. It's also using this library. This library is loaded here. Let's just copy this exploit here. Maybe it works. Maybe those addresses are still correct. So we have our exploit here. It's just a simple Python code, and we're just generating those bytes. Okay, so it's the same as I was using the command line. The reason I'm writing a Python script to do this is because it's a little bit more complicated. If we just write those numbers, we may get lost. So here, let's say what we want to input is just a string of bytes. First, we have 14 bytes of garbage to cover that buffer and 8 bytes of our saved RBP. So it can be A, it can be anything else. Doesn't really matter. That's garbage. Now after that, we have the first gadget address. The gadget is at this address. We need to double check if that's correct. Then we have those numbers. Okay, maybe they are correct. So let's just try. So if we need to make it executable. So now we can execute our exploit. So when we execute our exploit, so it should be temp e.python. So when we execute this exploit, it will generate those bytes for us, right? Then the program takes input from stdin, which is gets, which means we just need to pipe this into the buffer. Not buffer, the program. And looks like the address is not correct. So let's say the print secret address is 12C7, if that's correct. Oh, even that address is not correct. See, that address is changed. So we need to update this, but we need to see if the gadget's address are correct. So what we do is, let's say So that's why in our server, we installed a tool for you to find those gadgets, and that tool is called the Rob gadget. You can use this program to find that. Let's say. Wait. I should not copy the, oops. Let me just copy this part. Let me just use this part. There are many places we can find gadgets. We can find the gadgets in the program itself, but the program may not have many gadgets. We can try. Let's say we do buffer. This is a target program we are trying to exploit. If we're trying to find gadgets there, we need to do binary. So say the tool find 78 unique gadgets in this program itself. And those are just call-oriented gadgets, jump-oriented gadgets, and return-oriented ones. Okay. In this case, we only use the return-oriented ones. Okay, so those are the gadgets find. Not so many. But if we look for the C library, which is much bigger, then we may find more gadgets. And you can see the C library we are using is actually this one. So we just copy this address, copy this name. Then we try to find gadgets in this library. And we find 10,000 gadgets there, right? So there was an offset there when we loaded the program. That's offset. So you can see those address. Those are very small numbers. They are small numbers because they are only offset. They're not really the runtime address. So to get a runtime address, we need to put the offset there. So we do this offset. No, not this one. This one. Okay, so we do this. Then we will have the same gadgets, but this time we will have its runtime address there. So let's find what's the gadget we're looking for. We're looking for the gadget pop RDI return, right? Then let's just do the most easier way is just do a grep. We do a grep pop RDI return. Oh, sorry. Should do maybe a quote here. We do not find a gadget like this. It's weird. Okay, we do find the gadgets like this, right? RDI, let's say RDI return. Do we have one? Oh, yeah, there are two white space. That's probably why. Are we looking for RDI? Yeah, we are looking for RDI. Let's see. So this one actually may work. This one may work. So this one has a pop RDI return, and in the middle there are some other instructions, but we can trick it to not do anything. Oh, we don't have one. Let's see. Oh, here is one. RDI return, right? It's at this address, 1B72. Let's say in our slides, do we have the correct address? Nope. It's not the same. It's not the same address you see, but the end is the same. B72, which means probably the address changed after we reboot the system because there's a randomization there. But this should be the same gadget actually. So then we just copy this one. We go back to our let me get 2 terminals, I think. So let's get 2 terminals, and one of the terminals we will change our exploit, which is temp e.python, I believe. Okay, so we change this address to this. Okay, so we get our first gadget. The second one is not a gadget, is that value. So we only need this address, the third gadget, pop. So, I have to lost the history. So this will give us all the. There should be 3 zeros. What's going on? Oh, okay. Because I have 2 terminals. That's why when I copied that P there. Okay, this should be correct. Yeah. So we are looking for the second gadget, which is pop RSI. Pop RSI. What's wrong? There should be a pipe. Okay. We're looking for pop RSI return. Okay, we find one here. That's a gadget we need. Then we go back to our exploit, change this gadget address to this one. That's almost it, I guess. But that function address also changed. So let's run that program again to get the function address. Function address is 12 say 7. So we go back here to change to, say 7. Okay. Now we have our new exploit. Let's see if it works. It's possible that those addresses are not correct. Okay. If those addresses are not correct, then we need to go back to change. Oh, it's correct. Okay. So see, when we have those addresses, we actually got the flag. So then let's go back to, let's debug this a little bit to find out why this works. Okay. So far, any questions? Okay, then let's try to debug this to see why this works. I kind of forgot how to do this. So we debug the program. So let's set a breakpoint at vol_foo. Be vol_foo. Okay, there is vol_foo. Then we run this. Is this syntax correct? I'm not sure if the syntax is correct. Maybe it should be. Anyone remember the GDB syntax? Should be this way or the previous one? starting program this. Okay, ignore. Okay, so maybe the previous one was correct. Should be 3 or 1. Okay, let's see. Disassemble. So after gets, we are supposed to overwrite our buffer. So let's see if the overwriting is successful. Set a breakpoint there. We keep running. Now nope, it's not taking our input. So this syntax is not correct. What's the syntax here? So this will work, but okay. Okay, we can do that. What we can do is just execute our exploit and put it into a text file. Okay, so I have to write to temp. So now the text file has our exploit. Then we just redirect that into our GDB. So we GDB, we break points at valful, then we just run and redirect from temp.e.txt. So we're not running that Python script here. Anyway, it will be the same value every time. So after this, we now in valful this. So we want to go to the end of gets. Now we are at the end of gets, and it didn't ask us to type anything because this one already gave the input to the std. So after that, so now we technically should have our exploit on the stack. So let's just examine our stack. So examine maybe 6 items on stack. RSP should be $RSP. Okay. Yeah, it should be X value. Okay. So you can see that RSP is points to. So we are at we just finished override that, and you can say, oh, there may be some problems. So there may be zeros. Oh, zeros are here. Okay. So let's say where are our exploit? Where exploited are here? Our exploited are here. So those are the 8 uppercase A's, 41. So this one is actually the saved EBP. Then after that, we have 1B72, which is our first gadget. Is this gadget's address. This gadget's address is here. Then we have that 1, 2, 3, 4 thing. Then we have another gadget's address. Let's show a little bit more. And you can see after that we have the dead beef. After that we have the function address of the print secret. To prove that, we can do a p print secret, which gave us the address. And you can see that's the same, exactly same address. And if we examine those locations, if we examine this location, this is supposed to be our first gadget. So what added that location is supposed to be our pop RDI and return instruction. So if we examine 3 instructions from that address, you can see at that address, we actually have pop, RDI, and return. GDB default syntax is NTNT. That's why it has a $sign, but that's the same thing. So we are at here now. If we keep moving, we do SI, which we step 1 instruction. We'll go to the next line, then we go to the next line. Now we should add this line, which is a return. Now we're at a return, okay? So this is exactly where I showed you before at the beginning of this slides. This is where we are at. The RSP points to this address. The RIP points to this instruction, right? So now when we return, we're not going to return to the main function. Instead, we are going to return to somewhere has our gadget, right? So now we are already pointed to our gadget. How do we prove that? So say, right now we are at this location, 1B72. This location is in this function, elite cache info. We didn't develop that. That's part of the libc. And probably the instruction we are using is not an intended instruction in that function. I'm not sure. Let's say. So now we disassemble this. Let's say, do you see that? Where are we? So we are at, no. Which address we are at? Forgot. Which address? Let's say. So this one will give us the first address? No. It's probably not showing the arrow because we are in the middle of instruction. That's probably why. Let's say, let's do a print RIP. You can say we are at 1B72. And 1B72, oh, we're not there yet. 1B72. Oh, here. You can say, if we disassemble that function from the beginning, that's what the compiler intended to generate. The real instruction there starts at 1B71. And the real instruction there was pop register R15, then a return. That's the compiler generated instruction. But the pop R15 has 2 bytes, not 1 byte. Then we actually jump to the middle of that instruction, pop 15. And if we jump to the middle, we start from the address 1B72. It will not be interpreted as a pop R15 instruction. Instead, it will be interpreted as the pop RDI instruction. And that's what we want. Okay. So that's how we get that RDI. So if we keep executing, so this one, we're going to execute pop RDI. After that, RDI's value should be changed. If we change to RDI, print RDI, print X, you can see that's our value, right? 1, 2, 3, 4, 5, 6. So after that, we are going to execute another return instruction, and this return instruction, and bring us to the next gadgets. Okay, now we are in our next gadgets, which is at this address in another C library function. So if we disassemble here, 2529 here. If we disassemble here from here, then we go to 2529. You can see we actually jumped into the middle of another instruction. So here, the instruction we have is here, this one. The instruction we have is pop R14, and that's 2 bytes. If we go to the middle, we actually get we actually got pop RSI, and we are utilizing those 2 bytes to do this. We can also use online. Let's say online x86 disassembler. Let's just use this one to show you. We want to do maybe assemble. Let's do a pop RDI. And you can say, if the instructions are pop RDI, it is only 1 byte, which is 5F. If we do a R15, then it should be P, and it is 2 bytes. And the first byte is 14, the second byte is 5F. So if we jump to the middle, then the CPU interpret it as RDI there. We can do this one as well. Let's say 41 5F C3, right? So this should be interpreted as pop 15 return. But if we remove that 14, we start from here, that will give us what we want is pop RDI return, right? So that's how it works here. So after this, we keep going. Then this is the return. Then we keep going. And eventually, we go to the print secret function. That's what we want. And from the print secret function, if we say the 2 parameters, RDI, 2 arguments, RDI, oops, or the RSI, so we successfully set the value of them, right? Of course, right now it's in GDB. If we keep running, it's not going to give us a flag, okay? So even though we set up them correctly, even though we are entering the function print secret, if we continue running here, it will say, I cannot open the file. That's because we are debugging the program. When we debug this program, even though it's a set UID program, when we debug it, it loses its set UID ability. Basically, it's because GDB doesn't have that set UID ability. Okay, so if we run this outside of GDB, we are able to get a flag. If we run inside GDB, it doesn't give us a flag. Okay, so this is how the return-oriented programming works with this example. So in the software security class, we go beyond this. We talk about other more complicated cases. So in short, so ROP is kind of like you need to find the gadgets in memory. It's kind of like you find those smaller gadgets. They are kind of instructions. They are kind of Lego pieces. And they are innocent Lego pieces. They're from who is this guy again? No, this is Darth Vader. Yoda, right? Yes. So it's like you break Yoda down, get it smaller, the innocent pieces, and you use the innocent pieces to assemble something malicious. Okay. There are some useful gadgets. If you just want to skip some garbage on the stack, you can just pop them into the registers and ignore them. They are kind of like the no operation instruction in shellcode. Also, if you cannot fully control the stack, you can only control part of the stack. You can actually do a stack pivot if you can find an instruction like that, exchange RxRSP, so for example that. So this exchange instruction actually is very important to implement logs in the kernel because they do an atomic exchange of 2 registers. That's critical to implement log in a kernel. If you can, let's say, if you can switch RSP with some other register, you can change your stack to anywhere you want. Also, system calls usually those instructions are hard to find, That's why we can also use function calls instead of system calls. So we call the libc functions instead of directly making system calls. The tool we use, Rob Gadgets, actually, it can directly generate a Rob chain. The quality it generates is not very good. Sometimes it has errors, but it can generate a Rob chain like that to get a shell. I remember that's a default one. We have many other challenges on our server. For example, there is another overflow return 4, and the stack is not executable, 64-bit. To do that, we wanted you to develop a Rob-based exploit. That exploit will open a file directly, then print out the contents of the file. So in the previous example, return 3, I just showed you, there is a function called print secret in the address space. So you directly return to that function, and that function will magically print out the flag for you. However, in this example, that function doesn't exist. So you have to develop your own exploit or similar functions like that by writing some by chaining some Rob gadgets together. So basically, for that one, what we do is we will skip this part. So I will just show you. This is what the exploit will look like for that one. So you will make several system calls. Here you make function calls. You make 2 function calls. The first is a libc function, open a file. Another one is a libc function, send file. You can also do open and write, but it will be a little bit more complicated. Send file is actually also a system call. Most people do not know there is a system call called send file. Then after that, you can just the send file just make a. This is an exit system call actually. So this one doesn't matter. So this is open and send. So the exploit will look like this, and you need to make your flag, your stack look like this in that example. Okay, that's all I have for return-oriented programming. We do not want to go too deep in this course. If you want to learn more, go to the software security course. So next class, we talk about heap-based exploitation. Some of you took my software security course before, but maybe 1 year ago. If you took it 1 year ago, maybe I didn't talk about heap. But the newer version of my class have heap. We will talk a little bit about that next class. Okay. Any questions? What? Send the file? Well, you can use write. You can also use send file. Just use send file will be easier. So imagine when you write a C code, if you want to read something and you want to write to the terminal, one way to do that is you open that file, then you read that file, right? That's already 2 operations. One is open, another one is read. Then the third one is write, right? That's 3 operations. But coding in assembly it's kind of challenging, right? So we want to minimize that. That's why we do open, then send the file. Then there's no read operation, there's no write operation. Yeah, because if you do read and write, you also need to create some buffer in the memory. But now you are just you are attacker. It's anything you do there may crash the program, and you do not get what you want. Or maybe make it easier for other people to find you. So, yeah. I do have an exploit to do open, read, write. I do have exploit to do that, but sending it will be easier. Yeah.